This is the fourth video on rotation concerning angular momentum. Angular momentum is the equivalent to linear momentum for when we are rotating. Now, linear momentum, if you remember, was momentum equals mv. That's for linear. But if we want to look at angular momentum, we're going to change m to I, the inertia, the rotational inertia, and v to omega, just like we've done in many of the other things. And we use the symbol L for angular momentum. Symbol L for angular momentum. That equals I omega for a rotating body. Here I've got it summarised, and note that the unit is kilograms meters squared per second. They have never given another unit for that. It's just built up of the base units. You can always pause on these slides to make some notes if you would like to. There's another way of looking at angular momentum, and this is quite a difficult concept. If we have a small mass going past at velocity v, we know that that mass will have a linear momentum equal to mv. Now we're going to consider point x, which is not on the path that mv is travelling. Now with point x, we can say there's an angular momentum about point x. And you may say, but it's only travelling in a straight line. I know. I've drawn a circle there, and you can see at point y, it's just at a tangent to the circle. So we could say, just for that brief instant, it's travelling around the circle. Now if it was travelling around the circle, we'd say, well, it must have an angular momentum then. And that's how it's sort of looked at. It is a very strange concept, but it is useful and it does prove itself in experimentation. So we've got the mass moving along, and the mass goes past, as I said, in that instant at point y from point x, we could say that it's got a distance r, where r is the perpendicular distance. That means it's at a right angle to the line of path and that. And we say that that has an angular momentum of equal to mvr, the mass times the velocity multiplied by the perpendicular distance. Or if you want to think of it, angular momentum is the linear momentum multiplied by the perpendicular distance between the point and the path of the object moving. This is another aspect of angular momentum. So here we are, we've got angular momentum summarised for you, where it's linking to mvr. So just like with linear momentum, we have a conservation of angular momentum. And this happens where there is a collision or an explosion and there are no external forces or torques. You need to remember that. It's when there are no external forces or torques. So let's have a look at something here. Here's a person, and they run and jump on the roundabout, and their motion is converted to angular motion. So let's look at this in a bit more detail. Person at the start here has a linear momentum of mv. Compared to the centre of the circle, the centre of the merry-go-round, we have got them having an angular momentum equal to mvr, where r is the perpendicular distance of their path from the point of rotation. So here we go. Jumps on the merry-go-round and goes round. So this is the initial angular momentum. Let's have a think about the final angular momentum. So we're going to look at the final angular momentum. So we've got two parts. We've got the angular momentum of the merry-go-round, and we've got the angular momentum of the person. So we're going to have to add those two together. Now, the angular momentum of the merry-go-round will equal the inertia of the merry-go-round multiplied by its angular velocity. But what about the person? Now, the angular momentum of the person will equal the inertia of the person multiplied by omega. Now, the inertia of the person, because the person is small in dimension compared to the merry-go-round, we consider it as a point mass. And because we consider it as a point mass, we can say that the angular momentum of the person equals mr squared omega, where the mr squared is the angular inertia of the person. Because we're considering it a point mass, that's a small dimensional mass. It doesn't have to be small in kilograms, but it has to be small in compactness. So we can consider it a point mass. So we're considering the person as a point mass. So all that mass is at the one radius r. If the mass obviously is larger, then it will have a spread of radiuses, which will make a difference. Now, obviously, a person does have an amount of that, but we are considering the person as a point mass. So we can just assume it's all travelling at that radius r. Now, what we can say, then, for the final momentum will equal I omega from the merry-go-round plus mr squared omega. And if we look at that, then we can say this is equal to that, assuming we've got no external torques or forces. So let's look at this in summary. Here we are, the momentum, angular momentum at the start. After they've collided, we've got the angular momentum finally. So we can equate these two momentums, assuming there are no external forces or torques there. Now, this equation is interesting in the sense that we can measure m, we can measure v, we can measure r, and we can measure omega. So if we can measure all those things, we can actually calculate or give a good estimate of the inertia of the merry-go-round. Now, this is a useful technique to be able to do a quick estimate of what inertia might be. Now, obviously, there are some external torques and such like with merry-go-rounds because there's friction and various other things, but it gives us a good first estimate. This is a different scenario. With this scenario, what we've done is drop the block vertically onto a rotating disc. Now, it's initially rotating at omega I. We drop the block on, and we're saying the block sticks, so it doesn't slide or anything like that, and then it ends up rotating at omega F. Again, looking at the start, initially we only have the disc rotating, so this is for the disc. Initially, but finally, we have the disc at its new angular velocity plus the momentum of the small block. And again, we're assuming it's small compared to the size of the disk, so we're assuming it is a point mass, and we can use the mr squared. So we link the two together and we end up with this. And again, we could use this type of thing, assuming we know the measurements of omega I, omega f, and m and r. We could actually use this to calculate the inertia of the disk. Now, in addition to adding masses, which is what we've done in the previous two occasions, if we're talking about people, because people can move, we can change their inertia, their rotational inertia. So if a person moves their arms out, their rotational inertia increases. So this person here has a larger rotational inertia. So is increased by moving the arms outwards. Because we have increased the radius, so we have increased the inertia. This is increasing the radius. So we have increased the inertia. If we increase the inertia, and we're saying again that there are no external torques or forces, we must change something else, because we're going to say that this one and this angular momentums must be equal. And if we increase I here, omega must decrease to keep L the same. So what we've gone is moved from this person from here to here. We've brought our arms out, we've increased our inertia, so the angular velocity must decrease to keep L the same. Similarly, if we pull our arms in, going the other way, we would have to increase our angular velocity because our inertia has decreased, because the angular momentum must remain constant. And that's the important thing here, is the angular momentum is constant, assuming we've got no friction or such like things. Angular momentum is constant, so if we move from here with the person with the arms inwards to the person with the arms out, we end up changing the angular velocity to keep the angular momentum the same, because we've changed the inertia. So that again is something that's different from linear momentum, because we can't change a mass instantaneously, but here we can change inertia. And if you remember the boy turning here, if you look at the end bit when he stops sort of moving his foot to keep him going, he uses the principle of inertia by bringing his arms in line with the center of rotation. In fact, he raises the arms from out to the side to over his head so that they're in line there. And he increases his angular velocity, or at least keeps it going, because obviously we've got friction on the foot, which is taking it away. And that's what he's doing as he dances. And as I said before, dancing is one of the areas where they actually use conservation of angular momentum by changing the shape of the person. Now the energy changes, which we'll look at later, but that energy comes from the potential energy in the muscles.